Good morning and welcome to Tech 240 for Wednesday, April 14th. In today's class, we're going to take the topics that we've covered over the past week or so, capacitors and inductors, and we'll do something useful with them. And for today, that means putting them into filter circuits to make filters. But over the next couple of weeks, the last couple of weeks of this course, we're going to talk about a couple different kinds of applications for capacitors and inductors and AC circuits. The first application that we'll talk about today and next time is filter circuits. We'll talk about low-pass filter circuits today and high-pass filter circuits next time. And then after that, we'll talk about inverters and rectifiers. And then finally, in the last week of this class, we'll talk about how that fits into the context of the larger electric grid. So how we operate the electric grid as a whole. So we kind of got three different areas for applications of capacitors and inductors. And we're starting the first one today, which is filter circuits. But let's take a look at our schedule before we dive into filter circuits. And we can see that today on April 14th, we have Lab 15 due by 11:55 p.m. Lab 15 is the lab on capacitors. And remember, on Lab 15, I told you in the video last week that you don't have to do all of the problems in Lab 15. Remember, numbers 9, 10, and 11 in Lab 15, you don't have to do those. We didn't specifically talk about those. I know you can figure out how to do them based on the equation sheets that are given in the lab manual. So they're not impossible. You can definitely do them. They're not even that hard. But it's just a tiny bit beyond the scope of what I need you to be able to do in Tech 240. So that's Lab 15. Lab 16 on inductors is due next Monday, April 19th at 11:55 p.m. And one more thing that has a due date coming up is the last quiz in this class. Quiz 4. The very last quiz in this class is due on Sunday, April 18th at 11:55 p.m. Some good news about quiz 4. It will not cover the material that we're talking about today in class. So it only covers material that we talked about up to this point in the third section of this course, which is capacitors and inductors. So you can definitely expect some questions on quiz 4 about capacitors and inductors. All right, so that is about it for the schedule for right now. So now let's go ahead and start talking about low-pass filters. Basically, what filter circuits are is that they allow you to put in some type of signal, which could be noisy. It could be a noisy signal with lots of different interference and things like that. And you run it through a filter, and then you end up with an output signal that is much clearer, much cleaner, without as much interference and noise in the signal. We'll talk about low-pass filters today. Low-pass filters mean that they pass lower frequencies while they block or at least mitigate or attenuate, those all kind of mean similar things, the higher frequencies in that signal. So you got an input signal, you put it into a filter. If it's a low pass filter, it will allow the lower frequencies components, the lower frequency components of that signal to pass through the filter to the output, while it mitigates or attenuates or partially blocks at least the higher frequency components of that signal. When we talk about high-pass filters next time, it'll be the exact opposite. They will pass higher frequencies while blocking lower frequencies. So with that brief introduction, we can get started talking about low-pass filters. And to do that, I'm going to share my slides. So filters are going to be the topic for today as well as next class session. The really good news is that if you pay attention today and you grasp what we're talking about today, then next class session should be a breeze, because we're going to talk about low pass filters today, and next time we'll talk about high pass filters. High pass filters are pretty much the same as low pass filters, just kind of the opposite. They kind of do the exact opposite thing that low-pass filters do. So basically, what do filters do? Filters as a whole, whether they're high-pass filters or low-pass filters or a few different other types of filters, they let you clean up a signal, because signals are not always nice and clean and a nice even sine wave. They're not often like that. If you've ever been listening to the radio, I know people don't listen to the radio that much anymore. You have Sirius XM or something like that, but I still listen to the radio. I'm old-fashioned. And if you've ever been listening to the radio and you're driving a long way and the radio station starts to get out of range, so what happens? It starts to get kind of fuzzy, right? And kind of staticky. That's a noisy signal. That's a signal where the desired part of the signal is relatively weak compared to the undesired part of the signal. In the case of that specific example, that's a lot of high frequency noise. Static tends to have a lot of high frequency components to it. So you would want to use a low pass filter to get rid of the static. But there are plenty of other cases where you want to get rid of the low frequency part of the signal. That part is undesired, and you want to only have the high frequency part of the signal. So there's lots of different applications for low pass and high pass filters and other kinds of filters. My mind usually instinctively goes to audio systems, like sound, like your stereo system in your car or something like that. That's generally what I first think of when I think about filter systems, partly probably because I did a lot of my graduate studies on acoustics. So I've built a lot of filters like that we'll talk about today. I've built a lot of these with individual capacitors and inductors and resistors and things like that. So that's where my mind goes probably initially. But believe it or not, this is also applicable to visual systems like images, as well as video processing systems, and lots of control systems like motor control systems or robotics control systems. Think about your robotic system. You're sending a signal to the robot and you want it to move in a smooth fashion like this, right? Up or down or squeezing something or, moving around like that. You're moving your robotic arm, right? So imagine what would happen if you sent a fuzzy signal that looks kind of like this down here. Then it's kind of got some herky-jerkiness to it. Like it's not going to move as smoothly as you want it to. So these type of filter circuits are important for control system, lots of different control systems as well. So I just want to emphasize that it's applicable to a lot of different fields. It's not just audio systems. You want to clean these up because there's a lot of different ways that signals can become noisy. The largest source is interference from other electrical circuits. A lot of times that could be like a motor. Motors tend to produce a lot of electrical interference. So if you have wires that are running past a motor, chances are the signal that's running in those wires, even though it's not connected to the motor, it might have some interference in it because of the operation of the motor. Lighting, especially fluorescent lights, like I've got in here and most industrial settings have, or commercial settings, fluorescent lights are notorious for creating a lot of interference. And radio signals, we talked about that kind of already in the context of a radio audio signal and how it can be, interference can be introduced into radio signals just because they're far away from the transmitter. So this is kind of the idea. Here's a good picture to keep in your head. So this noise comes from lots of different sources that I just talked about. So it comes from interference. It comes from lots of different sources that are just really unavoidable. It's just not possible to create a signal that is nice and perfectly clean and smooth like this. So inevitably, your signals are going to have some noise in them. And so really, if you plotted your signals, it's going to look kind of like this. Sometimes a lot worse than this, honestly. So if you want to apply this to a speaker system, or you're doing some video processing, or you want to control a motor or something like that, with this, it's not going to sound as good or work as good as if you cleaned it up a little bit and got only your desired frequency output from it. Okay. All right. So that's basically why we need electronic filters, and that's how we would use them. So let's talk more about what they are. There's actually 4 different types of filters. We're really only going to talk about 2 of them, these first 2, because these last 2 are just built with combinations of these first 2. So the one we'll talk about today is a low pass filter. And as I already mentioned, it allows the low frequency part of the signal to pass through while reducing the high frequency parts of the signal. So that's actually the example that I just showed. So I'm going back a slide here. This is pretty high frequency. You know, it's going up and down really rapidly, whereas this is lower frequency. So if you wanted to clean this signal up and you wanted to remove the noise, you would pass this signal through a low pass filter. Okay, so it's going to reduce the high frequency parts of the signal, and the noise, in many cases, the noise tends to be high frequency, but not always. So a high pass filter is sometimes necessary when you want to remove the low frequency components of a signal. I would say this is probably a little bit less common than a low pass filter, but there still are plenty of applications where you need high pass filters. And this is just the opposite of a low pass filter. It allows the high frequency parts of a signal to pass through to the output of the filter while reducing or blocking or minimizing the lower frequency parts of the signal. The last 2, it's called a band pass and a band stop. And I think that would be best described if I just show you the picture in the next slide. So I'll save that for the next slide. And I do want to note at this point that you can make all of these filters. You can make them with different combinations of resistors and capacitors, and we call those types of circuits RC for resistor capacitor filters. Or you can make all of these different types of filters with a combination of resistors and inductors, and we call that RL, because R is for resistance and L is for inductance. It's the symbol for inductance, as we talked about last time. All right, so you can make an RC low pass filter, or you can make an RL low pass filter. Similarly, you can make an RC high pass filter or an RL high pass filter. And those are the 4 things that we're going to talk about between today and the next class session. Today, we'll talk about RC and RL low pass filters. Next time, we'll talk about RC and RL high pass filters. This is kind of what it looks like if we have frequency plotted on the horizontal axis and amplitude or voltage of the signal on the vertical axis. What a low pass filter does at lower frequencies, it will allow that signal to pass through kind of unmitigated, unabated, whereas it will attenuate. The word we usually use is attenuate. It's not really blocking. Sometimes we'll say that, but that's a simplification. Because what we're going to talk about is something called a cutoff frequency. And for right now, you can just think about the cutoff frequency as being right around this knee right here. And for a low pass filter like this one, generally it's going to pass unmitigated or unattenuated, the low frequency portion, and it's going to attenuate the high frequency portion that is above that cutoff frequency, about right there. All right. A high pass filter does kind of the opposite. Here's about the cutoff frequency right here for a high pass filter. So the frequencies that are below the cutoff frequency for a high pass filter will be attenuated or mitigated, blocked, I guess, if they're really low frequency. So band pass is just a combination of a high pass filter and a low pass filter put together in a certain way that it allows only frequencies within a narrow frequency band to pass through the filter. And band stop is the exact opposite. So in this case, you would have a low pass filter here and a high pass filter here, and that would cut out the frequencies in a certain range. So let's say let's say you're collecting, I don't know, let's say you're collecting acoustic signals on the rooftop of the building, and there's a there's a constant humming sound from a motor, from a nearby motor. All right, and that motor emits a constant pitch. You know, it's like a constant hum. So that constant pitch you might want to remove from your signal. So you could do that with a band stop, because you could identify what that frequency is that you want to remove from your signal, and you could create a band stop filter that is a pretty narrow removal, has a pretty narrow removal window for a specific frequency of signal. All right, so for all the filters that we talk about today and next class period, we're going to want to know what's the cutoff frequency, and more specifically, we'll talk about what does that mean? What is the cutoff frequency? For right now, you can generally say, like I just said, that frequencies above the cutoff frequency for a low-pass filter are attenuated. Frequencies below the cutoff frequency for a low-pass filter are not significantly attenuated. So that's what the cutoff frequency is. We'll talk more about it in a minute or two. The other thing we're going to want to know about these filter circuits that we're going to talk about is, what is the output voltage for a specified input voltage and frequency? So what I mean by that is, the input to these filter circuits is realistically going to be a combination of a bunch of different frequencies. So what we're asking by this question is to say, all right, let's take the portion of the input signal that was 100 hertz. What's going to be the output voltage for that portion of the signal? So let's say the input signal was 20 volts and it had a lot of different frequencies at it combined to form the input signal. So for the portion of the signal that was 100 hertz, or right around 100 hertz, what's going to be the output voltage of that portion, just that portion of the signal? All right, we'll talk more about that in a little bit. All right, we're going to talk today about low-pass filters, and there's two different kinds of low-pass filters that we will talk about. There are more. There are other kinds of low-pass filters, but we're just going to, in this class, focus on RC and RL low-pass filters. So those are filters that only have resistors and capacitors, or resistors and inductors. So we're not, there are, if you look it up online, there are other kinds of low-pass filters that are beyond the scope of this class. So we're just going to focus on these. The RC filters tend to be more common than RL filters. And that's true for low pass as well as high pass filters. RC tends to be more common than RL. The reason for that is, if you do the math and you figure out the necessary sizes of the inductor and capacitor necessary for a specific cutoff frequency, you'll find that the capacitor is a lot cheaper and a lot easier to work with than the inductor that gives you the same cutoff frequency. All right, let me say that one more time. If you are trying to make a filter with a specific cutoff frequency, all right, so you know you want to make a filter that has a cutoff frequency of 100 hertz or something like that. So let's say you want to make a low pass filter with a cutoff frequency of 100 hertz. You could make an RC low pass filter with a cutoff frequency of 100 hertz, or you can make an RL low pass filter with a cutoff frequency of 100 hertz. But if you figure out the sizes of the components that you'll need, the resistance and the capacitance, or the resistance and the inductance, what you'll find out is that it's a lot cheaper and easier to build the RC circuit than it is the RL circuit. So for that reason, RC circuits tend to be more common, but both work and both are, in existence and in use in the real world. All right, so this is a review. This is not new. Think back 1 week ago when we talked about capacitors, and we talked about the reactance of a capacitor. And we said that the reactance of a capacitor, X sub C, capacitive reactance, is equal to this equation. This is what we gave a week ago. 1 divided by 2 pi fc, where f is the frequency of the input signal, and c is the capacitance of the capacitor in farads. Oftentimes microfarads, could be millifarads, something like that. So usually it's going to be much smaller than 1 farad. So notice what happens when the applied frequency increases. if we increase f, what happens to x sub c? If we increase f, this number gets larger, the denominator gets larger. If you divide by a larger number, then your result gets smaller, right? So as frequency increases, the reactance, this, decreases, right? The opposite of that is true as well. As f gets smaller, you're dividing by a smaller number, then x sub c increases, all right? But stick with that first thing that I just said for right now to follow the train of thought. As the frequency increases, the reactance decreases. And if the reactance decreases, if the reactance of the capacitor decreases, in an ideal capacitor, there is no resistance, all right? So I mean, in a real capacitor, there is a little bit of resistance, not a lot, but a little bit. But for an ideal capacitor, we can say there is no resistance. Therefore, for a capacitor, when the reactance decreases, we can say the impedance also decreases, because remember, if we have a circuit that is purely capacitive, then remember we said we could use V equals Ix instead of V equals Iz, where Z was impedance, X was reactance. If there's no resistance, in the circuit, then the reactance is equal to the impedance, all right? We said that last time, just refreshing your memory here. If there's no resistance in the circuit, then the reactance equals the impedance, all right? They're the same thing if there's no resistance, okay? What impedance is the AC version of resistance. So impedance is the opposition to AC current flow. So the capacitor is going to give a decreasing impedance, that is a decreasing opposition to AC current flow, as the applied frequency increases. All right, this is really important to understanding how an RC filter, any kind of RC filter, works. You need to understand what happens to the impedance in a capacitor as the frequency changes. So what you can take away from this equation right here is that as the frequency increases, then the impedance, this is reactance, but the impedance is going to decrease. As the frequency increases, impedance of the capacitor decreases. Okay, that's what it says right here. Frequency increases, decreasing impedance. Here's what an RC low-pass filter looks like right here. We have the input applied right here. So this is our noisy AC input signal that has probably lots of different frequencies all combined. And we want to just get the low frequencies out. Well, we want to mitigate or reduce the high frequency components of that signal. So this allows us to do that. What happens in this filter is that all of the frequencies, the whole signal, passes through the resistor, but then the important part happens right here in the capacitor. Remember that for the capacitor has decreasing impedance as the frequency increases. All right, so its opposition to current flowing is lower for higher frequencies. So the high frequency components of the signal, after they've passed through the resistor, the high frequency components of the signal, this basically acts like a short circuit. They're just shorted to ground. So the high frequency components have no problem going right through the capacitor and to ground. And they do. That's what they do. So because they're just shorted out by the capacitor, we don't even measure that right here. It's like that. It's like it's just shorted to ground directly for the high frequency components, but only the high frequency components of the signal. Meanwhile, the low frequency portion of this signal also passes through the resistor, but they can't pass through the capacitor, at least not nearly as easily. Those low frequency portions, they're blocked by the capacitor. They can't pass through as easily. And so that serves as our output. All right, so basically you can sum this up by saying the high frequency portions have no problem going through the capacitor, so they just go through that into ground. So we don't even see those in the output. Meanwhile, the low frequency portions of the signal can't pass through the capacitor, and so they pass through to the output. So when we're measuring our output of the filter right here, our reference is ground, and our input side right here, I shouldn't say that. This is the output, not the input, but what we're measuring across right here is from this point to ground. And on this point, we see all of the low frequencies from the signal, but we don't see the high frequencies from the signal because those high frequencies have all passed through the capacitor to ground. All right, so that's kind of summed up down here. The whole signal passes through the resistor. The capacitor has a decreasing impedance. That means opposition to AC current flow as the frequency increases. So therefore, the high frequency portion of the signal just goes right through the capacitor as though it's not even there and goes to ground. Whereas the low frequency portion of the signal is blocked, or it can't pass through the capacitor as easily. And so it passes on to the output because it has nowhere else to go. All right, now we'll talk a little bit more about cutoff frequency, because notice I don't really like saying blocked because the cutoff frequency is kind of misnamed. It's not like it passes frequencies up to a certain point and then all of a sudden, boom, it blocks all the frequencies above that. It's hard to design a circuit that does that. Certainly this type of RC low pass filter doesn't do that. What it's doing is above the cutoff frequency, it is increasingly attenuating the amplitude. So if you've got a really high frequency up here, then your output voltage for that frequency is really, really low. Whereas if you've got a frequency that is below the cutoff frequency, then it doesn't attenuate the signal nearly as much. So it's just kind of a convenient point. The convenient point that we define, it's a little bit arbitrary, but the point that we define as being the cutoff frequency is the frequency at which the output voltage is equal to 70.7% of the input voltage. So if this is the cutoff frequency, the amplitude in voltage, the amplitude of this signal right here at this frequency is equal to 70.7% of the original signal's voltage. All right, so 70.7% is the cutoff. It's defined as the frequency where the output voltage is only 70.7% of the input voltage. For frequencies higher, they're more attenuated, or they're more increasingly cut out of the signal. For frequencies that are lower than the cutoff frequency in a low pass filter, then they are less attenuated or less reduced, if at all. All right, so that's what we mean by cutoff frequency. And the equation for cutoff frequency is pretty straightforward. For any RC filter, this is the cutoff frequency. So the cutoff frequency is equal to 1 divided by 2 pi RC, where R is in resistance in ohms, and C is capacitance in farads. So you might have to put, for 100 microfarads capacitor, you'd put 100 times 10 to the minus 6 farads. Or if you're putting it into your calculator, 100 e negative 6. That's 100 times 10 to the minus 6. And the cutoff frequency is measured in hertz because it's a frequency. The other thing besides cutoff frequency that we want to know about a circuit, we want to know what's going to be the output voltage for a given input voltage at a specific frequency. So let's say we've got a filter, and let's say that our input signal is, let's say it's 200 hertz at 20 volts. What is going to be the output? What's going to be the output voltage of that signal? And we can figure that out because the way these operate is actually very much like a voltage divider. And hopefully you might remember that from the first third of the semester. If not, maybe go back in the lab manual. It's really quite easy. It's very easy. The voltage divider for a DC circuit, like we talked about in the first third of the semester, says that the voltage drop across a resistor is proportional to that resistor's resistance as a fraction of the total resistance in the circuit. All right, so quick example to jog your memory. Let's say we got a DC circuit, so no capacitors or inductors or anything. DC circuit, you got a 10 volt voltage supply, and I got 2 resistors in series because the voltage dividers only work when they're in series. So we have a 10 volt voltage supply. We have R1, let's say, is 4 ohms. And let's say R2 is 6 ohms. I'm making the numbers easy here. And they're wired in series, all right? 10 volt voltage supply, R1 is 4 ohms, R2 is 6 ohms. What's the voltage drop across R1? What's the voltage drop across R2? All right, if you remember voltage divider, that's super easy because all you have to do is take the resistance of that resistor as a fraction of the total resistance. R1 plus R2 is 4 ohms plus 6 ohms, which is 10 ohms. And if we want to know the voltage drop across resistor 1, then we take 4/10, because the total resistance is 10 ohms, of the input voltage. So 4/10 of 10 volts is 4 volts. So the voltage drop across resistor 1 would be 4 volts, and the voltage drop across resistor 2, which was 6 ohms, would be 6/10 of 10 volts, which would be 6 volts. All right, so that was the DC voltage divider. The filter here operates exactly that way, because just neglect the output for a second. Really what we've got here is a circuit right here. We've got an AC circuit. We have a source right here, and these two components are in series. And yeah, we can measure the output, but the output is only the voltage drop across this capacitor right there. And we can measure that, and we could use that as a supply. But when we're talking about the output voltage, we're just talking about the voltage drop across this capacitor. It's just a little bit different now because it's an AC circuit and not a DC circuit, but all that means is that we have to use impedance instead of just plain old resistance. All right, so we know what the impedance of a capacitor is. A capacitor is purely capacitive. At least that's what our assumption is, and it's pretty good. So the impedance across this, I shouldn't say across, the impedance of this capacitor is equal to the reactance, which is 1 over 2 pi FC. And in order to get the total impedance of this circuit, we did this a week ago, the total impedance of this circuit is the square root of R squared plus X sub C squared, or the capacitive reactance, which is the same as the impedance of the capacitor squared, all right, which is this equation right here. So this equation right here is nothing but a voltage divider for an AC circuit. Here's the input voltage right here. Here is the impedance, which is the same thing as reactance because our capacitor is purely capacitive. And that is the impedance of this component. And the denominator here is the impedance of the whole circuit. And that's what we did a week ago when we talked about impedance for RC circuits. That's part of the reason why we did that a week ago. All right, so here's your formula for the output voltage at a specified frequency. So in order to find what the output voltage is for an input at, say, 200 hertz, we would plug that 200 hertz frequency into here to find what is the reactance and thus the impedance of the capacitor at 200 hertz. And then we'd plug that into here and into here and solve for the voltage output. All right. All right, so that's it for RC circuits. All right, that's more than half of the battle because RL filters, are very similar. They just use inductors instead of capacitors. So if you understood RC circuits, RC filters, then you're well on your way to understanding RL filters. For an inductor, remember a few days ago in the last class session, we talked about the reactance. For an inductor, it's 2 pi times the frequency times the inductance, which is measured in henries, and the variable is L. So here, note that as the frequency increases, the reactance increases. And if our inductor is purely inductive, then the impedance is equal to the reactance. All right, so if the reactance increases, then the impedance also increases. So we can summarize that by this last statement. Inductors provide an increasing impedance, which is an opposition to AC current flow, as the applied frequency or the applied signal as its frequency increases. All right, so it does not want to allow high frequency signals through it. it does easily allow low frequency signals through it. All right, and this is a circuit diagram that's kind of similar to the RC low pass filter, but go back and check and you'll see that they're a little bit different. Remember, the RC low pass filter had a resistor here and had a capacitor right here. All right, so be careful about the placement of these components. So what's going on with this signal? We've got our input voltage here, and we know that the inductor has an increasing impedance to higher frequency components of the signal. So it's going to block and not allow high frequency portions of the signal to pass through. It's going to attenuate the higher frequency portions of the signal. Meanwhile, it has low impedance to low frequency components, and so it's going to allow the low frequency components to pass through it. All right, so only the lower frequency components of the signal are allowed to get through the inductor and make it over to this point right here. The resistor, the only point of this resistor is to provide a voltage drop, and we can take our output across that voltage drop. All right, so that is the purpose of this resistor, and that's where our output is measured right there. So we can take that output, and it's going to have most of the high frequency components removed from the input signal. All right, the cutoff frequency, same definition. It's still the point at which it's the frequency at which the output voltage is only 70.7% of the input voltage. The equation is a little bit different. Remember, the cutoff frequency for an RC filter is 1 over 2 pi FC. The equation for the cutoff frequency for an RL filter is R, the resistance in ohms, divided by 2 pi L, where L is the inductance in henries. And FC is still in hertz. Just like for an RC low-pass filter, when we have a RL low-pass filter, we also want to be able to know what is the output voltage when we have an input voltage at a certain frequency, all right? Or what is the output voltage for the portion of the signal at a certain frequency, all right? Kind of means the same thing. So fortunately, this works very similarly to the RC low-pass filter in the sense that it's a voltage divider. And remember that what a voltage divider is for a DC circuit, we can say the voltage drop across a resistor is proportional to that resistor's resistance as a fraction of the total circuit's resistance, right? That was the DC voltage divider. Now we have an AC voltage divider, so we're using impedance instead of just resistance. So if we're taking our output across this component right here, this resistor, what the voltage is going to be, it's going to be proportional to the impedance of this component, and it's just a resistor, so it has no reactance. So the resistance is equal to the impedance. They're the same thing, all right? If it has no reactance, then the resistance is equal to the impedance. Remember that triangle where we had the resistance and the reactance and the impedance. If one of the legs is 0, then the impedance is equal to the length of the other leg, whatever it is. All right, so the impedance across this component is just equal to this resistor's resistance, and the total impedance of this circuit is exactly what we did in the last class session on inductors. It's equal to the square root of R squared plus the inductive reactance squared. And remember the inductive reactance, remember this from last time, same equation as from last time. The inductive reactance is equal to 2 pi times F times L. All right, so this looks really similar but not identical to the equation that we had for an RC low-pass filter. All right, so a little bit of review. This is going to be about it for low-pass filters. So we're going to fill the rest of this in next time. But in today's session, we talked about low-pass filters, both RL and RC low-pass filters. So first of all, you got to remember what we did a week ago. You got to remember the equation for capacitive reactance and for inductive reactance. Remember, the equation for capacitive reactance is 1 divided by 2 pi Fc. And the equation for inductive reactance is X sub L equals 2 pi FL. So you got to remember that from last week. Don't forget that. But once you know that, there's really only 2 equations that are very relevant for us for each of these circuits. I want you to know what the cutoff frequency is, and that is 1 divided by 2 pi RC for an RC filter. And the output voltage is equal to the input voltage times this ratio right here, capacitive reactance divided by the square root of R squared plus capacitive reactance squared. All right, that's the output voltage at a specific frequency for an RC low-pass filter. For an RL low-pass filter, the cutoff frequency is the resistance R divided by 2 pi L, where L is in henries again. And the output voltage, we just talked about this, is equal to the input voltage times this ratio of the resistance, which is equal to the impedance, since there is no reactance for a resistor, divided by the square root of R squared plus the inductive reactance squared. All right, so that is it for low-pass filters. That is all the new material for today. We talked about RC low-pass filters and RL low-pass filters. And so I'm going to cut off this video in just a minute, but I'm going to make a second video. There won't be any really new material in that video, but what I'm going to do in that video is help you out by giving you a tutorial of the program that I want you to use to complete labs 17, 18, and 19. That's the 2 filter labs and the rectifier lab. And I'll talk about that software program a little bit more in the next video. I would say the downside is that this Multisim Live program might not be quite as intuitive as Tinkercad, so it's maybe a little bit more difficult to play around with it and learn it from just playing around with it. You still could. It's still relatively intuitive. But I think it'll help you out and save you some time if I make this tutorial video. So I'm going to do a tutorial video about Multisim Live, and I'll even show you a low-pass circuit in the program. So that's what I'll do in the next video. So that's going to wrap things up for this video. I'll see you in the next video.